Okay, so thank you very much. I'm very pleased to be here. And in particular, I've never worked on localization of waves, so it was a very good meeting for me to learn a lot of things. And if someone was worried that his talk was to low level, I mean, my talk would be more elementary than yours, so don't worry. And in particular, I'm talking about numerical analysis. So I'm a mathematician, I'm an applied mathematician working on numerical analysis, finite elements. And I will try to give you my insight on the approximation of eigenvalues starting from very, very basic examples. And well, I hope this could be of some help also for the future of the project, perhaps. And some keywords of what is my research about. Of course, scientific computing, this is what all about. Error analysis, so we want to see from the numerical point of view what is the difference between the exact solution and the approximate solution. And this is very nice because I worked all of my career trying to mimic with the numerics the reality. And I learned from this workshop that there are people that do it the other way around. I mean, they use the numerics as a reference solution and they try to construct reality that approximate the numerics. So this is a very nice two-way direction. Well, anyway, we will talk about some errors, and in particular we'll try to show you where numerical analysis can be wrong sometimes. And this is what we usually teach our students. And probably you also have seen something like that in your numerical analysis courses, but I think it's useful also to understand how things can go wrong sometimes. And finite elements, I already told you about that, so this is my main expertise, and I'll try to give you some idea on how it works. And adaptivity. So this is actually cutting-edge research, and I will do something like that at the end of my talk. And when you have, of course, waves, and waves are very much localized in some place, as you would like to have. When you approximate your domain, it's useless to waste a lot of energy to approximate the solution when it is flat. It's much more important to approximate it when you have peaks, when you have local phenomena. And adaptivity exactly is what is doing that for you. We try to refine your mesh in some local region and not in other regions. And then we try to give you some ideas, in this case, how things may go wrong from my point of view in some situation. And as I said, I never worked on that, but I try to get some insight on how this machinery worked about. And then the last keyword I learned here during this meeting, and well, let's hope that this is not the case. And this is the outline, if I can go through all of it. And I will start with something very basic, as I said, just the algebraic eigenvalue problem, 2 by 2 matrices, and then I will go larger and larger and up to infinite dimensions, and then try to give you my point of view about localization of eigenfunctions. So let's start with algebraic eigenvalue problem. Well, this is just to set the notation. So of course, everybody knows what is an eigenvalue, what is the spectrum, and what is the characteristic equation to define, to compute the eigenvalues, right? And there are some invariants, you know. This is just the basic of every linear algebra course, trace determinant, and diagonalization. I would like to spend some time on that, which is also something very basic, but just to give the first difficulty that I can see in some situations. Well, this is very clear. I mean, if you have to solve AX equal to lambda x, if you take S to be a matrix which is column-wise the eigenfunction, then you have this equation, right? And what usually people in linear algebra teach you is that if S is is a non-singular, then you can invert it and you get a diagonalization like this. And lambda is the matrix just formed by the eigenvalues on the diagonal. Okay? And of course, the polynomial, the characteristic polynomial is preserved by this diagonalization, and this is what you know. And how can it be that the matrix is not diagonalizable? Well, of course, you need to take a matrix when you have some repeated eigenvalue, because of course, if all eigenvalues are simple, then the eigenfunctions are orthogonal to each other, so the columns of the eigenfunction, the eigenvectors form a regular matrix. And this is a simple example. When you have a repeated eigenvalue, it's a triangular matrix, so you have 3, 3. The algebraic multiplicity of this eigenvalue is 2, because the characteristic polynomial has a double root at lambda equal 3. This is very basic. And if you want to write everything in the form of diagonalization, the matrix S can be chosen in many different ways. This is 1, because the eigenfunction, the eigenvector corresponding to 3 is 1, 0. So it's this column here. Then you can put 0, 0 if you want, or you can put any multiple of 1, 0, and this is what everybody knows about the difference between geometric and algebraic multiplicity. Okay? And in particular, this is not diagonalizable. From now on, this is I think what also you want to do. We consider matrices that are diagonalizable. It's clear. Now let's try to get involved with some error analysis. So let's take a 2 by 2 matrix like this one here. Very easy to compute by hand. The characteristic polynomial is this one here. So in particular, you can compute the diagonalization as follows, and the eigenvalues are 1 and 2, like this, very easy. Let's try to perturb it a little bit, make a little change in one of the entries of your matrix. Instead of 101, you take 100 here. Okay? This is the new polynomial to get. There's a huge difference. Instead of 2, you have 100 here. And instead of 3, you have 2, which is the error in this coefficient is the same order of the perturbation. But here from 2 to 100 is a much bigger error, of course. And the new spectrum is completely different from the previous one. So instead of 1, 2, you have two conjugate complex numbers. And the error from this previous solution and perturbed solution is of the order of 10, say roughly speaking. Okay? So you make a perturbation of 1 over 100 relatively, and you perturb the solution by 10. So it's a huge difference. Okay. Why am I telling you this? You know, all of you know about that.
Actually, it's pretty cool.
So I'm telling you because, I mean, you have to be careful. I mean, when you do numerical analysis, you get...
It's like to show to all students, you know.
Exactly.
Yeah.
This is what I usually do. So that's and, well, so when you put the matrix in the computer, of course, there is some round-off error that is very small, and you don't care, because it's, well, -10, -16, well, it's a small number. But then the real error can be amplified by a factor which is pretty large, even on a 2 by 2 matrix. So suppose now you take a million by a million matrix. The error, of course, is much larger because you have many more operations that you have to do. The round-off is bigger, and, well, you can, of course, cook up problems where the sensitivity is much higher than this one here. Okay? So you have to be careful. Is this a problem for us? Of course, you're worried about that? Probably not, because there is, fortunately, a good theorem that in some particular situation, the error is not so bad. And this is the famous Bauer-Feig theorem in the 60s that tells you that if the matrix is diagonalizable, the previous one was, but let's see. If you perturb A by a perturbation matrix delta A, and if you could with tilde the perturbed quantities and without tilde the original quantities, then you have this estimate here, that this minimum is bounded by this quantity. So there is a multiplication of 3 norms. The norm of the perturbed matrix, which is the thing that you want to put on the right-hand side. So you would like the error to be of the same order of the perturbation in some sense, roughly. Okay? And then you have these 2 norms, norm of S and norm of S inverse. Okay? Well, there are some cases where the product of these 2 norms is 1. Fortunately. And the good cases are when A is a so-called normal matrix. Okay? And normal matrix includes symmetric, skew-symmetric, orthogonal, Hermitian, unitary matrix. And so if your problem is, in some sense, in this category, then you don't have this problem. But you have this problem, but it's not so serious as in the previous slide. Because if you commit an error in your matrix, then your solution is perturbed by something which is of the same order of the error that you commit. So if your error is round off or something like this, then also the eigenvalues are perturbed by round off or something like that. So I'm talking about exact solution. I mean, you're just solving by hand, not by the computer.
I have a very different question. That's probably what you're saying in your paper, just to double check. Isn't while inequality exactly that the eigenvalues are perturbed only a little bit when the matrix is perturbed a little bit?
Which inequality, sorry?
While. For Hermitian matrices, there is an estimate that the perturbation of eigenvalues is controlled by perturbation of the matrix.
There is a constant, the constant is 1, or there is something? Here the constant is 1.
For the sum to be Hermitian as well.
This is what's the conclusion?
While inequality controlled
Yeah, what am I
perturbation.
about to say?
Huh?
Oh, in the while inequality, you need the sum to be Hermitian as well. Here, A tilde has no structural assumptions, right? I mean, in his example.
Yes, the perturbation can be whatever perturbation, yes.
Yeah, but factually, when you do it in, for example, PDEs, you are plugging in, I mean,
No, your roundup errors don't have any structure.
Can be done, so.
there are many exceptions. We use it at proofs all the time, so it's a different, yeah.
But it's wrong.
But it's actually, well, I would argue with that, but it's a different.
Okay.
So it just stays in the symmetric class, or it stays in whatever
I
class.
mean, you know what I mean, right?
Well, I mean,
You use it all the time, I mean, it's perturbed. In Anderson localization process, you perturb a little bit, then you value perturb a little.
right, but you're just staying in the symmetric class.
You are staying in the symmetric class.
Okay.
It's the perturbation.
Here the perturbation, I mean, A tilde has no structure. I mean.
Yes, so
So-
the point is that perturbation of potential doesn't screw it up, perturbation of matrix might. So that was my confusion. If you are approximating Schrödinger, you can perturb the potential and will be fine. Might not be able to
Sure.
perturb the entire matrix.
Yes, there are
You
many.
don't have to worry, you can perturb it any way you want. The original matrix is Hermitian and
Right.
an eigenvalue is a constant one, two-dimensional number.
Yes, it was impressive, and while, and I don't know.
Okay, so anyway, here we are talking just about perturbation of matrices and exact solution. So we're not talking about solving numerically the eigenvalue problem, just talking about the property of the matrix. Okay? So there are several sources of errors and we have to trace all of them. And well, since everybody put some quote, I also put one. It's from Wilkinson. And you can read it if you want, but the last two lines probably is the more important. I mean, determination of accurate solution presents a wide variety of challenging problems for eigenvalue problem. And this was in the 60s, but I'll say that the same quote can also be transferred to our days. I mean, I think this will be also probably the main message of my talk. I mean, there are a lot of challenges from the numerical point of view in approximating eigenvalues. And this is the main reason why I'm using my computer, because now I'm trying to give you some computation with MATLAB online, and with a very easy matrix, with a diagonal matrix, like the one that is written there, with some repeated eigenvalue. So I showed you before that when there is a repetition of eigenvalue, there might be some problem with algebraic multiplicity and so on, but here there is not, because it's diagonal. So there is no problem. Algebraic multiplicity is the same as geometric multiplicity. And I cook up a matrix where I have 1 repeated as many times as I want. There is a parameter I can change in my code. And then a k plus 1, k plus 2, up to n on the diagonal. So very easy. Okay? And I will compare two solvers of MATLAB. One is EIG, is the most common one. It deals with full matrices and is used QR decomposition for solving the eigenvalue problem. So it computes all of the eigenvalues. Okay? And then I compare with EIGS. S stands for sparse matrix, so it uses a sparse matrix structure. It uses some sort of Arnold iteration for computing the spectrum, and it solves only a part of the spectrum. This is what you usually want to do when you have a lot of eigenvalues and a very big matrix. So if your matrix is very large, you don't want to spend so much time to compute all of the spectrum. You just want to concentrate on the part you're interested in. Okay? And in this case, I will try to solve for the k plus 1 first eigenvalues. So in this case, I would try to have 1, 1, 3 as a solution. Okay? And let's see how it works. So this is MATLAB. I have a code that is test, matrix dimension. Let's start with some easy example, 10 by 10. Dimension of the first eigenspace, so I mean how many repetitions I have at the beginning. Let's put 3. Okay, that's fine. So this is the order of the solution, 1, 2, 3, 4, and this is EIG, and this is EIGS. So far, so good. Okay. Let's try to make the matrix a little bit larger. Then I put, say, 30. So I have to run the code first. It was too easy. Okay, 30. Dimension of the first eigenspace. Let's start with 3 again. Okay, that's good. Fine. 30 again, and let's put 5 instead of 3. Oh. This is a very small matrix. 30 by 30. And I'm asking with EIG to compute all of the spectrum. So it gets the correct ones. And with EIGS, I ask to compute only this one that you see here. Okay? This was not k plus 1, but k plus 2. Okay? Then you get 1, no, it was k plus 1, because it was 1, 1, 1, 1. Here it should be 1, but there was no 1, 6, and 7. So it misses 1. It misses 1. It's a big error. It's a huge error. Okay? And if you go higher with the dimension, suppose now we take 100 instead of 30, I think that, let's try, 3 is not enough, but 4 I think will be. Yes. So this is a 100 by 100 meters, a little bit bigger than before. And now the first k that breaks the code is k equals 4. Before it was 5. So the larger you go, the smaller the k.
It seems like it messes up less on the k plus 1 eigenvalue than it does on the kth eigenvalue.
Yes. The rest of the spectrum is perfectly approximated. So what is wrong is just here.
It just misses one.
Is the multiplicity that breaks the code, actually. So the problem is that when you compute all of them, of course you're looking for all of them and you find them. If there is a multiplicity missing, you realize that there is something missing. I'm talking about intuition, right?
So the problem is spectral gaps, basically.
The problem is that when you compute only these eigenvalues, you start with an eigenspace of dimension 5, this is an initial guess, and then there is some machine that gives you the solution. And the minimum, the optimization in the code gives you a 3-dimensional eigenspace and then 2 simple eigenvalues. And there is also another solution, which is the good one, with 4 and 1. But you pay more to get that one than to get this one here. And then the solver finds this one. And is happy with that, because the tolerance is enough for him to stop. So this is, and since I've heard during this workshop about a sparse spectrum, a dense spectrum, sorry.
But there shouldn't
I mean,
be
you cannot, I hope not.
it should go by wire, again by one of the pieces. There is one
This is a diagonal matrix.
There is a one probability which tells you exactly how far for self-Schrödinger perturbed still self-adjoint.
Yes, but you know,
It's a diagonal matrix.
But this is
Yes, but the
very
question
serious.
is,
serious.
the question is perturbation is still in the same.
No, it's not even that. That
You're
is
putting
solver.
it with diagonal
You cannot
matrix
even trust the solver.
You can't trust
But
the
diagonal
no,
matrix-
also for other matrices you can hook up. So, and I don't have example. I stopped here with the numerical example, then I would go with some more theory. But the problem is that when you approximate things, being equal or being close, when you have a discretization parameter, from the numerical point of view is the same. When you have some mesh size h, and your difference between the spectrum, between the eigenvalues is of the order of h, claiming that the two numbers are the same or they're different is very difficult. So it's like if you're looking something with the wrong lens.
But the problem is exactly that we are looking for resonant 12. In the case of resonant 12, we are exactly in this case.
Or if you were in a semi-classical limit, you basically just have the V operator in the limit. The V operator could be 1, 1, 1, 1, 1, 5, 6, 7, 8, 9, 10. It could be exactly that.
Yeah.
So what algorithm should we use?
Well, the QR works. Here, but even if you use more sophisticated softwares, I mean, if you use LabC, which is probably the state of the art for solving eigenvalue problem, is parallelizable, all you want, and so far, you can use any preconditioner. You face this problem if you compute only one part of the spectrum. So this is, I mean,
The difference is that the first one computes the entire spectrum and then
Exactly.
takes out
This is the
the
difference.
values, and the second.
this is the difference.
But on the other hand.
Well, you can play with the tolerance of this solver, and then the problem is less serious. But you have to know that you're facing this problem. So there is no indicator that tells you that you're doing something wrong. So if you notice that solution, then you know that something's wrong. You can go back to your code, change the parameter, and find a good solution.
So I think Doug has been using programs that also insist that you have a spectral band, that it's, you're only looking for eigenvalues between 0.99 and 1.01.
Yes, but you're never sure that you get all of them,
You're never sure that you get all.
because you don't know the dimension of the,
Yeah, you don't know.
you don't know how many they are.
Absolutely.
So what you find is in that window, but you cannot guarantee that you find all of them.
This is point one.
So
What is the complexity of QR?
QR is n cube.
Thank you.
Okay, so I think I can go back to the previous page. And here we are. And now let's go a step further. And from matrices, now we go to differential operators. Okay? And well, just to give some setting, I'm usually working in Hilbert spaces. There is a linear bounded operator T, and T is compact if the range is relatively compact in H. This is well known. And typically, in differential operators, this comes from the fact that T actually has range included in V, which is a compact subset of H. In the case of Laplacian, H would be L2 and V would be H1, H10. Okay? This is basically an example. So T is the solution operator that a given F tells you what U it is. Okay? And definition of eigenvalue, you know about that. You start with defining the resolvent set, then the complement is the spectrum, and the eigenvalues are the point in the spectrum, in the element of the spectrum such that the kernel of T minus mu I is different from 0. And you know the theorem that characterizes the eigenvalues of compact operators that tells you that 0 is the only element of the spectrum, then all elements different from 0 are eigenvalues. Okay? And then you have that all non-zero element of the spectrum, that the eigenvalues are either a finite set, or is an empty set, or is a sequence that tends to 0. This is the characterization that you know. And then you have also this nice definition of algebraic geometric multiplicity and this ascent multiplicity that is related to the kernel of the iteration of T minus mu I. Okay? So this is, I assume that you know about that. And in particular, there is the spectral decomposition of compact operator, which plays the same role as the diagonalization of matrices that we've seen before. That tells you that in the case of a self-adjoint operator, for instance, there exists a Hilbert basis of H consistent eigenvector. This is exactly the matrix S that you have seen in the matrix example before. In the case of, let's now play with some easy differential operator, Laplace, 1D, the easiest we can do. Okay? And T is going to be an operator from L2 to L2. Let's assume you take the interval 0 pi, so we don't have pi in the solution. And this is our equation. Well, this is the equation that is satisfied by eigenvalues and eigenfunctions, of course. Then the eigenmodes of T, well, T is the solution operator, so the eigenvalues of T are going to be the reciprocals of the eigenvalues of your differential operator, because you are going in the other direction. Okay, so T of F is equal to U in the notation of the differential operator. So if M square is an eigenvalue for the differential operator, 1 over M square is an eigenvalue for the operator T. The eigenfunction is the same, sine of Mx for M going from 1, 2, and so on. And in particular, sine of Mx is well known that it's a Hilbert space for the L2 in the interval 0 pi. Okay? And if you want to approximate this, let's start now before finite element with well, the easiest brother, which is or sister, which is finite difference. And what is the discrete problem associated with this one here? So if you take, for simplicity, a uniform partition of the interval 0 pi of size h, let's look at this general line of our system. You approximate the second derivative by a finite difference. This is the usual 3-point formula for the second derivative. And then you put on the right-hand side lambda ui. Okay? So for I ranging from 2 to n minus 2, you have this equation. The first point, u0, would be 0 because we have Dirichlet boundary conditions. So the first line is the line corresponding to u1, not to u0. And you don't have u0 here because it's 0, so you have only this part of your system. And the last line is for n minus 1. You don't have un because un is equal to 0, again for the other boundary condition. And then you have this equation here. Okay, so this is very, very basic. And if you write it in matrix form, you have this tridiagonal matrix divided by h squared. This is the vector of the unknowns equal lambda vector of unknowns. Okay? And well, it's well known that A is symmetric, positive definite. And it's very easy to compute the solution by hand. You don't need to use a computer to do that. Just guess that you have the exact solution at the nodes. This is what happens also for the source problem in some particular situation. So you can guess, in particular, if the solution is smooth enough, this is what happens for the source problem. Since the solution is analytic in the case of eigenvalue problem, you can guess that you have this. So you claim that ui is equal to the sine of MIH, Okay? It's just the interpolation at the nodes. And then if you plug this solution into this system, magically I disappears. And so this means that this is a solution. And you find this formula here, that you have lambda m, if you want, equal to this expression here, this quotient. And of course, the asymptotic expansion of this quotient is just m squared, okay, because we have h squared on the denominator, plus order of h squared. So, good. So this shows you that you have, for each m, an eigenvalue of this matrix that converges towards m squared, with a speed which is equal to h to the square. So second order convergence. Okay? This is very easy to show. Let's go to finite elements, just to see that finite elements is something also plausible. So you need a functional space. Let's take h10, which is the natural space for this equation, multiplied by a test function, integrated by parts. This is your variational formulation. Okay? The usual variational formulation for the Laplace. And what is now the difference with respect to what we had before? Well, the difference is that now we not only have a matrix on the left-hand side, but we also have a matrix on the right-hand side, coming from this term here, a mass matrix. So this will be the algebraic structure of our problem. Well, as long as m is invertible, this is not a problem. You just multiply on the left by m inverse, and you get a standard algebraic problem. And you can compute everything by hand. And there is some magic here, but everybody working in this field knows it pretty well, that the matrix for finite elements is just a multiple of the matrix of finite differences. There is only a different scaling. Instead of 1 over h squared, you get 1 over h, and this is due to the fact that we are integrating instead of differentiation, basically. But this is not a problem, because the mass matrix on the right-hand side scales like h. So the h squared, which is not here, is compensated by the h which is on the right-hand side. And this is the structure of the matrix on the right-hand side. But if you repeat the same computation that by hand that we did before, you can also find the exact solution by hand. And the only difference is that now in the denominator you have this term here, 2/3 plus 1/3 cosine mh. Well, again, the asymptotics is the same as before, because this red term goes to 1, so there is no problem. Okay? And let's see now what does it mean in terms of numbers. If we now put these numbers in a computer and try to see how is the approximation with finite differences, finite elements. So the blue is the exact solution, is a parabola, m squared. Okay? And for n equal 2, you only have one eigenvalue, which is very easy, very close to 1. Then if you increase your approximation, you are putting more and more points. Okay? So then discrete level, you find more and more values. And these are the ones that you find. So this is finite elements. And finite elements are always an upper bound for the exact solution. This comes from the minimax problem that we've seen before. In the case of elliptic equation, the minimax property gives you a monotonicity of the solution.
This is with I or with H?
This is exact solution by hand. So I use the formula that I computed by hand by guessing the eigenfunction. Okay? And the final difference is from below. I didn't know that. I found it, but I don't know. I tried to Google if there is a result on that. I don't know. I don't know if Doug knows about that. But I mean, final difference are a lower bound for the exact solution, and I don't think it's a general rule. I would guess it's not. But in this particular case, this is what happens. And if you go on with the size of your matrix, so you put more and more points, well, clearly you get a better approximation of the lower modes, and you start getting some approximation of the higher modes, but here you see a typical behavior of the approximation of eigenvalue of differential operators. I mean, even with 96 points, a pretty dense mesh, it's a pretty fine mesh in one interval, in 1D. So you get a pretty good approximation up to the 20-25 mode, but then there is some error. Well, the error is order h squared. We proved that before. But there is a constant in front. And this constant depends on lambda. And the higher lambda, the higher the constant. With 128, you get something better. With 256, you're still off for the 60th eigenvalues, for instance. Okay? And of course, if you're interested now not only in the fundamental modes, but also in the higher, there is something better that has to be done, because this method of clearly is not very efficient. Okay?
I just like to say that my collaborators who asked me, would you compute the first 10,000 eigenvalues? Should be paying attention now.
go 2D. Okay, 1D was too easy. So 2D, Laplacian in 2D, 0 pi by 0 pi, because I don't want pi in the solution again. And well, variational formulation is what you are expecting. Now this solution depends on two parameters, m and n. Is again a parabola, but in 2 dimensions. And this is what you get if you just take a triangulation of your domain and triangles without any structure, just a Delaunay mesh. And now what is the difference between 1D and 2D? Well, in 2D you have multiplicity. So if m is equal to 1 and n is equal to 2, you get the same value as if you reverse m and n, of course. So 5 is a double eigenvalue. And if the mesh has no structure, since of course the multiplicity comes from the symmetry of your domain, if your mesh is not symmetric, it's not strange that you don't find the multiple eigenvalue at discrete level. But asymptotically you get convergence. So they separate, the difference between the two becomes smaller and smaller, and asymptotically they tend towards 5. Okay? And if you look at the corresponding eigenfunction, so this would be one representation of the eigenspace, just the membrane that vibrates in one direction and in the other. And if you look at the eigenfunctions, this is the coarsest mesh that I used, and you see that there is some splitting of the two components, even though, I mean, come on, there is a huge difference. So here I chose a representation of the eigenspace because it's a two-dimensional eigenspace, and I could choose any combination of the two. Okay? Here I don't have any choice because they are not multiple, they are separated. So the code gives me two different eigenvectors. I cannot mix them up because they correspond to two different frequencies, to two different eigenvalues. Okay? And here's what I get on the first mesh. And then you see on the next mesh, there is another splitting which is similar to the previous one but not exactly the same. And here you get another one again. So it's difficult to claim that this sequence of eigenvectors converges towards something, even if you multiply by plus or minus 1. So clearly here you have something which is opposite than the other one. Of course, if you have a normalization, you can normalize. You can multiply by plus or minus 1. But here you see there is something on the diagonal. This is not exactly something that follows the same track. And if you go on, you get more and more of this behavior. And this is more evident if you now take a structure mesh. So a mesh that has a structure. And here, again, they split. But if you look at the eigenfunction, you see that the eigenfunction align with the mesh. So it's clear that the composition between the two eigenspaces depends on the mesh, even though the two discrete eigenvalues are different from each other. And this is even more clear if you now take a symmetric mesh, a crisscross mesh like this one here. Now the two approximations of the 5 are superimposing, I mean, at the same value, because now you preserve the symmetry. This makes sense. I mean, this is what the physical intuition tells you. And some theoretical framework, but then I want to go to something more serious. Well, this is the technique that we use to prove the convergence of these things. So you already introduced the Hilbert space and the compact operator. And the general eigenvalue problem is written like this, with the two bilinear forms A and B. And the solution operator, I introduced it before. This is the general definition for a bilinear form A and B. Then you have this continuous set of eigenvalues and eigenfunctions. You decide to normalize them using the bilinear form B. Okay. There are many different options. Then you have the discrete problem with a number of eigenmodes which is equal to the dimension of the discrete space. Then you have the discrete solution operator, which is always compact because it's a finite dimension, of course. And then you have a finite set of discrete eigenvalues and eigenfunctions. And then how do you say that the discrete modes converge to the continuous modes? This is also something tricky. It's not so immediate how to define that convergence. Well, first of all, you have to tell people that there are no spurious modes, and I will show what a spurious mode can be. So take any compact set in the resolvent set of the operator. Then for h small enough, you would like that this compact set is also in the resolvent set of the discrete operator. So if you take a region where there are no eigenvalues of the continuous operator, eventually there should be also no discrete eigenvalues in the same set. This makes sense. Okay? But then you have also to say something positive, so to say that the correct values are approximated, and this is the statement. So if you take a non-zero eigenvalue of your operator t with algebraic multiplicity equal to m, then you claim that there are exactly m discrete eigenvalues of the operator th that repeated according to their algebraic multiplicities, such that mu I h tends to mu for all I in this set from 1 to m here. Okay? They could be repeated because the mesh could be symmetric or not, but the important thing is that you are counting them according to their multiplicity. And moreover, how do you define the convergence of the eigenspace? This is the more tricky part, the most tricky part, because now you cannot use just any single eigenvector as I showed you before, so you need to consider them all together. And you have to introduce also, if you want, you may introduce the notion of gap, which is the angle between Hilbert subspaces, just to compute the distance of normalized things. And what you claim is that you have convergence whenever the gap between the continuous eigenspace and the direct sum of the discrete eigenspace tend to 0. So you have to consider them all together at the same time, not just one. And this is an example of how things can go good or wrong. So on the left, in each box, you have the multiplicity of a continuous eigenmode, 3, 1, and 2. And on the right, you have the corresponding discrete frequencies, eigenvalues approximating it. So this is the good setting. This is what you want. This is what may happen. There is some missing, but this is also what can happen. There is some spurious one, some more than you need. Okay? And I will show you an example of this spurious immediately. So how do you define the convergence? Well, the convergence is guaranteed whenever you have this convergence in norms, whenever the difference between t and th goes to 0 in norm. This is a standard perturbation theorem. And in particular, in the case of self-adjoint operators, this is a if and only if. So this is nice. And so in general, the strategy would be, first, you prove this uniform convergence. So you have that you have convergence. And then you want to estimate how fast. And then you have to estimate the order of convergence. And in order to estimate the order of convergence, well, first, this is the tool that they usually use in order to prove the uniform convergence. You use the property of the elliptic projection. So TH can be seen as the elliptic projection applied to T. This way. So T minus TH is nothing but the identity minus PH applied to T. So if you know that the identity minus PH converges pointwise, and if T is compact, they are put in the right order. So you have the compute operator applied first, and then the operator that tends to 0 pointwise. This combination converges strongly, so you have a uniform convergence. So this is what has been proved by Colata in this theorem, and this is a consequence actually of Banach-Steinhaus. I think I can say Banach-Steinhaus in Europe. In the States, I have to be careful because they don't know the name. They call it uniform boundedness principle. It's the same theorem. Okay? And you know it. Okay. The first time I mentioned Banach-Steinhaus in the States, nobody knew about that, but that's good. And this is the proof, but I'm not showing you the proof because I don't have time. And the order of convergence depends on the approximability of T and the adjoint of T. So if epsilon h is the rate of convergence of T minus TH, and if epsilon star is the rate of convergence of T star minus T star H, but notice, not everywhere, just restricted to the eigenspace or to the adjoint of the eigenspace. So this is important, I mean, because eigenvalues may correspond to eigenfunctions with different regularity. And then this epsilon can be different according to the regularity of the solution. And the speed of convergence of lambda depends on the regularity of the corresponding eigenfunction, this way. And this is the theorem that says that the error in the eigenvalue is just the multiplication epsilon times epsilon star raised to the power 1 over alpha I, where alpha I is the ascent multiplicity of the eigenvalue. In particular, in the case...
What do you mean by the adjoint of the eigenspace? You mean
is the eigenspace of the joint operator. Is the corresponding eigenspace of the adjoint operator.
At level 5?
At the same, yes.
Oh, okay.
Yes. And so the gap for the eigenfunction goes to 0 with order epsilon h, and the order for the eigenvalues is epsilon times epsilon star. In particular, for self-adjoint problem, you have double order of convergence for the eigenvalues. So this is what we have seen in 1D for the Laplacian. We had h squared with first order scheme. So the eigenfunction is converging with order 1, but the eigenvalue converging with order 2. So this is the important conclusion. So if you take any standard Galerkin approximation, this is good, I think, in the case of Schrödinger, because Schrödinger is an elliptic operator, so you take any approximation that is good for the source problem, then theoretically, this works also for the corresponding eigenvalue problem. With all the warnings that I gave you before, of course. The higher frequencies are difficult to approximate, which makes sense because are highly oscillating, and that the solver can produce some additional error. Let me give you one critical example and then go to localization very quickly. The critical example comes from Maxwell equation, which is, the model that probably I studied most in the framework of eigenvalue problem. You know, you're teaching me what Maxwell equation is, so I don't have to tell you what it is. But in the time harmonic regime, it is standard to go to the curl-curl operator. We've already seen there is also some poster talking about this. And let's consider epsilon mu equal to 1 for simplicity, because all the troubles already arise in the very simple configuration. And what is known in the framework of finite elements is that you need some special finite elements for the approximation of this eigenvalue problem. So standard finite elements don't work, and I will show you why after giving you the variational formulation. So the standard variational formulation with epsilon mu equal to 1 consists of taking functional space H curl, so it's the space of vector fields in L2 with bounded curl. And this not here means that the only trace that makes sense in the distributional sense is 0, so the tangential component is 0 of the boundary. And curl u curl v equal lambda uv, because you multiply by v, you integrate by parts, and you get curl curl linear form. There is no minus sign in the case of the curl. And this is the weak formulation for the divergence-free constraint for you. Okay? And I call the solution u instead of electric field or something like that, because I'm a mathematician, so I forget about where the equation comes from. I just look at the differential equation. And the most commonly used, actually, variational formulation for solving this problem here is to forget about the divergence-free constraint, because the divergence-free constraint at the numerical level produces some troubles. So since you have Helmholtz decomposition, if you forget about the divergence-free constraint, what happens? You're just adding a big kernel to your operator. All gradients belong to the kernel. And suppose we are in simple topology, so we don't want any harmonic forms or something like that so far. And the spectrum of this operator here is exactly the same as the previous one, with the only difference that here you're adding a big kernel, an infinite dimensional kernel. Okay? So if you require lambda to be different from 0, then you get rid of the kernel and you get an equivalent problem. So, and this is actually what people were doing. We're just approximating this problem instead of this one here in order to avoid the divergence-free constraint. And if you try to do that, okay, let's do it in 2D. The solutions are the same as the Laplacian in this particular case, because we have 2D is actually the solution of the curl of cos. I mean, these are the curl of the solution of the Neumann problem for the Laplacian in this case. And if you do this with standard P1, this is what we get. As I told you, people know that the standard finite elements don't work, but this is surprising actually, because I just told you that for the standard elliptic case, give me any method that works for the source problem, and this will work also for the eigenvalue problem. And here, actually, we need something better, because this is what you get with the coarse mesh. You refine, you see that you have a lot of bad frequencies here. So the exact solution should be infinite number of 0 that you get rid of, and then you have the correct ones, isolated from each other. And here you have a lot of frequency, and going up to 50, you don't reach 1, which is the lowest frequency. Okay? Then if you zoom in, yes, you find the correct one. And how did I detect that these are the correct one? Of course, by looking at the eigenfunction. If you look at the eigenfunction, you see something like this. You see that this is bad, this is good, and this is bad. But this, of course, is not a good method for solving this problem, okay? And you can go higher, and you find something like this. And there are some magic. There is no proof for this. There is a very particular mesh for which things are good. These are the guys that invented this, but this is not something we can generalize in 3D or something like that. But what is good in this mesh is that it has a locally supported basis for C1 function. Because you need to take the gradient of something to be in the kernel, So if you have C1 pieces polynomials that are supported on this mesh locally, then you take the gradient, this will be a P1. So you have a lot of P1 on this mesh that are in the kernel, and this is the dimension of the kernel. So in some sense, you have a good splitting between 0 and the rest of the spectrum. And then there is another compatible mesh, and also on this mesh, we have a nice splitting of 0 and non-zero. And if you look at the result, this is what you get. You get a number of 0, which is increasing as h goes to 0. This is good. Then you have good values that they're approximating the correct values with a good order, 2. And then you have something wrong. So this converges to 6. Nice second order convergence towards 6. But 6 is not, of course, an eigenvalue of the nominal Laplace, because it would imply the square root of 3 is integer, and this is probably not the case, right? And and then there are other spurious modes here. Okay? And this is the picture of the spurious mode. I told you that I would go to meet some spurious mode, and this is what you find. And just to give you the interpretation of the spurious mode very quickly, we could compute them explicitly by using not P1 but Q1. That means that you're taking a mesh of squares now instead of triangles, and bilinear elements. So just the tensor product of P1 in 1D and P1 in 1D, P1 in X and P1 in Y. And if you use just Q1, you get something bad, like with P1. But if you could use Q1 and you project the curl onto pieces constant, by some magic, you get a nice formula that looks like this. So you can order all the discrete frequency with m and n in such a way that you have the corresponding eigenfunction, which is just the interpolation of the exact eigenfunction multiplied by something that goes to 1. So this is very nice. And if you look at the formula, when h goes to 0, this formula clearly goes to m squared plus n squared. This seems to be very nice, because this goes to 0, the denominator goes, this goes to 0, this goes to 0, this goes to 0, so you have 1. So it remains m squared plus n squared, 4, and then you have h squared, and there is some 4 coming from the denominator, I think, that I cancel out this 4. Anyway, so you get m squared plus n squared. And you might think that this is good convergence. Then you compute things, and you get this. So you get a spurious frequency. So 18 should be a simple eigenvalues, the mode 3-3. Okay? But you get 2 of them. But we just proved that we are convergence. So what's wrong? The proof or the numerical examples? Neither. They're both correct. In the sense that the proof is wrong, actually, because it's not enough to show that for fixed m and n you have convergence. Because now if you compute this limit, when you relate h to m and n, you get exactly 18, which is the spurious one. And this is the picture of what you get. Let's look at this way. So this is you're looking at the diagonal of this graph. So the exact solution would be a parabola, m squared plus n squared. And this is the distribution of the discrete eigenvalues. And here is the diagonal. So if you look at the diagonal, when n increases, you see that each red dot is approximated by some black dot, and this is good. So you have pointwise convergence, and this is what I showed before with the theorem. But then this tip here, this tail, goes to 18, and this is the spurious value. Because if you now sort your discrete values not with m and n, but with just the usual sorting, it's at the smallest to the biggest, then this 18 stays in the middle of the spectrum and remains there. Okay, so this is another tricky situation that may happen with approximation with finite elements. Very quickly, localization. You know these pictures, and I wanted to present a couple of examples, so probably will present only one. Let's see what I can do. But this is the idea. I mean, I'm talking about adaptivity. The idea that I mentioned at the beginning was to try to refine your mesh locally when you need it. So, and this is the paradigm for adaptivity. And I'm using what is called Dörfer strategy. So the idea is that you have these inputs. So you start from an initial triangulation, tau 0, and the parameter that is called also refinement parameter or bulk parameter, what you want, theta between 0 and 1. And the idea is that if theta is larger, you are refining more. If theta is smaller, you are refining less. So it's something that tells you how much you are going to pay at each refinement. And what is the output that you want to get? So you want to get a sequence of meshes that are refined adaptively, but what is going to be filled here inside. So a sequence of meshes, a sequence of solutions on these meshes, and a sequence of estimators. So there is some estimator that a posteriori tells you how good was your computation and where in your domain. What is in between? In between there is a standard solve, estimate, mark, refine strategy. So you first compute the discrete solution at level L, and this is the solve part. Then you estimate. This means that you compute some estimator, which is local and cheap to compute, of course. You don't want to pay too much. So locally, you are computing something that tells you how good was your approximation there. Then you mark. And this is where theta plays a role. So you mark a fraction of your elements according to this inequality. So as I said before, if theta is equal to 0, you don't mark anything because it's always satisfied. If theta is equal to 1, you mark all of them in order to get this inequality. Okay? And you mark those elements where the error is bigger, in such a way that a fraction of your error is going to be reduced at the next iteration, because potentially reduced because you're refining your mesh there. And then you refine, so you generate a new triangulation such that all the marked elements are refined. And then perhaps you have to spread the information a little bit to preserve the conformity of your mesh. And what the theorems that we usually prove for these things, so I can show you also a theorem just to tell you that, not just telling you some stories. It is stated in terms of nonlinear approximation classes. So there is a standard way of defining how a function can be approximated by approximating function, piece of polynomials, for instance. And your idea would be that your adaptive scheme, using the PDE, the estimator, all the stuff that I showed before, should give you the same rate of convergence as if you just want to approximate that function without any PDE. So you know the solution, by chance, and then you want to find the optimal mesh, theoretically, that gives you a good approximation. And actually, this is what you can do. So you can usually show theorems like this, where you have that the gap between the exact eigenfunction and the discrete eigenfunction is bounded by some norm of your eigenfunction space times the cardinality. That means that how much you paid raised to the power minus s if you bring to the right-hand side, which is exactly the optimal s that you get if you just want to approximate the function. So your adaptive scheme provides you with the same rate of convergence as the best approximation that you can do in terms of number of degrees of freedom. So these are theorems that you can prove in this framework. Okay? And moreover, the eigenvalues are approximated with double order of convergence. And question. I'm going to localization. I'm just showing this picture, and then I don't know how much time I have. 5 minutes, right? Something like that. Everybody took something more. And so let's take the square annulus. So here you have a situation where lambda 2 is equal to lambda 3, everything is symmetric. And you can decompose the eigenspace in such a way that lambda 2 has a singularity on the top left and the bottom right corner, and lambda 3 has a singularity on the other two corners. Okay? Now suppose we want to cook up some adaptive scheme in order to approximate this eigenfunction, one or the other. What would be the best adaptive strategy? An estimator based only on lambda 2, an estimator based only on lambda 3, an estimator based on both. It's clear from what I said at the beginning that it's difficult probably to separate one from the other. Okay? But it's clear that adaptivity according to this singularity calls for refinement at two corners. Adaptivity for the other eigenfunction calls for refinement at the other two corners. So if you're only interested in one of the two, approximating the other one asks for more work that is not needed. But this is the example, this is what you do. I mean, if you try to refine according to lambda 3, here we are using, sorry for the confusion, non-conforming elements, and in this case we have approximation from below. So we don't have the minimax. In case of non-conforming means that we are using P1 that are equal only at the midpoint of the faces and not everywhere. So in this case, you don't have conformity, you don't have the minimax problem, so you're approximating from below. And here you have the eigenvalue, and here you have the level of refinement. And if you refine according to the higher, everything goes good. I mean, you have a good approximation of the third one, and not so nice approximation of the second one, but you don't care, because you wanted the third one. Now if you, and these are the corresponding eigenfunction, and this is what you can imagine. But now, suppose you want to approximate lambda 2 instead of lambda 3, okay? So you are here. Here, because of the symmetry of the initial mesh, the decomposition between U2 and U3 comes from the solver, not from the eigenspace, because it's the same double eigenspace, and you refine according to U2. Okay? Then you have this situation that your mesh now is not symmetric anymore, and at the next level of refinement, they split these two values, and this is the third one, and this is the second one. And we decided to refine according to the second one, which is the one that is worse approximated. So now you are working, improving the approximation of this one here. And actually at the next level, this has improved, and the other one has not, as should be. Here again, they are by chance multiple, and we have the same situation as before, so they split. But now this is the second one. We improved this one here. So basically, you see, we have a situation where the two frequencies, the two eigenvalues, swap at each time. And you can see that very clearly if you look at the eigenfunction. So here, this is the first eigenfunction corresponding to lambda 2, and this is the second eigenfunction. On the next refinement, you get the other eigenfunction, because they change position in the spectrum, because you improve the approximation of one, and you are not improving the same level, the approximation of the other one. On the other hand, if you work on both, you get something very nice. This makes sense. And what has this to do with localization? Last example, and then I'm concluding. Let's take my example of localization, two L-shaped domains that are connected by this small corridor here. And they're not completely symmetric. There is a slight asymmetry, so that the first four modes are exactly at this value here. So there is almost a double eigenvalue as a fundamental mode, and then something else. And this is computed on a very fine mesh, so it's pretty reliable. Okay? And if you start, now suppose we are after the second frequency, the second eigenvalue. First mesh tells you that it's here, localized on this region. Then you refine here. And now the second eigenvalue is there. Then what do? You refine there. Okay, and then you come here.
Yeah.
Take some time before it stabilizes. And so we are already 10,000 degrees of freedom. Now you don't see anything because of the mesh. So let's remove the mesh so you only see the pictures. Okay, now the split. So this means it might happen that even if they are different, not the same, there is a mixture of the two frequencies, of the two corresponding eigenfunctions.
So they were different, the eigenvalues.
This is one eigenfunction. Yes, they were different.
And if you were
They were different.
But the numerical one is not localized.
Exactly.
Oh, shit.
Well, it's still-
And it was localized on coarser mesh.
Yeah.
I guess each time you go closer, you underestimate, right? Systematically.
Yes, because it keeps changing position. They
When you
keep-
refine one, it gets.
You refine one, so this improves. You see, here we're after the second one. This was the first and the second one. Okay? So you have, let's make it larger. So this is lambda 1, and this is lambda 2. They are very close, but let's put it far away so we can see how it works. And then on the first mesh, you have something like this. Now, this is the second one, and this is the first one. They both are upper bound, so they're good. So you are working on this, so you are improving the approximation of this that goes there. And you are not improving the approximation of this one that goes like this. Now the second one is this one. And then you refine again. And in this situation, probably they are very close to each other. Probably they're multiple, or multiple with lengths corresponding to the mesh size. Okay, so they are very close compared to H. And then you keep going. Okay, the correct answer is this one here. So the second one is on the left. But it took 500,000 degrees of freedom to detect it.
And
Okay.
you put so much work into getting a good mesh, but in the end you got your mesh refined everywhere, right?
Exactly. So this is a little bit disappointing, but this is my understanding about what numerical analysis can do. I mean, what is the state of the art of numerical analysis? So there is a lot that the numerical analysis can do. So this is good news, actually, because my conclusion is that this is the sentence that I mentioned before, but the good conclusion is that so far we know what we don't know. And I think this is a good message for mathematicians.
understand it's sort of an ill-posed question, but I'll try anyway. So we face all the time same problem of, what our matrices look like, sort of tri-diagonal, and one of the diagonals is random, so overall it's super sparse. And there appears a question virtually every time after my talk on a new audience, how much faster it is to compute the landscape versus mean solve AU equals 1 or ratio equals 1, however you want to call it, versus to find eigenvalues. And I understand that this depends on the method, but let's say, is there any complexity theory, meaningful response, or this state-of-the-art methods, whatever that means? I mean,
So-
should you comment on this from your point of view?
If the question is only how expensive is to compute the landscape versus eigenvalues, I think the answer is clear. So the good question would be how expensive is to compute the landscape up to a reliable result compared to eigenvalues up to a reliable result. Because, also landscape is affected by this phenomenon. You need refinement somewhere to
Yes.
get a good landscape.
Yeah, so let's say with the same
Okay, I would say that landscape is cheaper, clearly, because it's just one solve of a source problem. And the iterative scheme that I mentioned before for the eigenvalues, so each iteration involves a solution of a linear system. So for landscape, you solve only once. With eigenvalue problem, you have to solve many times, but if you're not interested in all of the spectrum, but in a part of it, you are solving a smaller system. But then, I don't know, there is no theorem that tells you what is the threshold between number of eigenvalues and so on. This, I think, it would be probably something that this project could investigate in order to. But
So it's very
I don't know if
important
Doug
for us to
knows
be
something
able to
more,
say
but-
something systematic about this.
Well, I just say that you have to talk about, you have to compare getting landscape to getting a certain number of eigenvalues. You even have to say sort of which eigenvalues. It's much easier to find the largest eigenvalue than it is to find one in the middle, for example, if you only want one eigenvalue. I don't know what your experience is with the source problem versus finding just one eigenvalue. I tend to think of those as maybe differing within at most a factor of 10 or something like that. It's not that much more expensive to find one eigenvalue than it is to solve a source problem. But when you want to find 1,000 eigenvalues,
Yes.
it's not 1,000 times more difficult, but it's significant.
But I guess my question is, it would be good to introduce some parameter and be able to answer it at least in quasi-mathematical way, not 10,000, 100, but there is a size of the matrix there, what we are solving, size of the domain, there is a number of the eigenvalues. Let's say, roughly speaking, if we are doing the square potentials, as many as there are invisible potential for the eigenvalues, which is roughly speaking divided by 4 or whatever what we are interested in. So there is a parameter to it, and it would be good to have some meaningful answer with, polynomial, the parameter exponential, and the parameter.
You'll get a much more meaningful answer by using the stopwatch and running both computations and measuring the time.
Yes, but time should be in terms of the
There's
parameter.
so many factors that affect the fate of this. So many different algorithms you can use, so many different solvers, each one with different tolerances and so on. It's very hard to say something mathematical like that.
I fully realize that, but any sort of, it's sort of the same thing as it's hard to prove the theorem, but let's start with the baby theorem. It's the same thing. There must be some baby statement which we can give when people ask that, and people ask that literally after every talk. So there must be some meaningful statement other than, stop by Doug's office.
That's how much harder it is to prove Anderson localization than Line's law. Hard to quantify.
So this was the last question.